Hi, my name is William, and in this video I'm going to present joint work with Quan Chang on derandomization.
Randomized algorithms are good, but deterministic algorithms are even better. The goal of derandomization is to start with randomized algorithms and try to find deterministic algorithms that do the same job. For example, we would like to design deterministic polynomial time algorithms for languages in BPP. Recall that BPP is the class of problems that can be solved in randomized polynomial time, where we allow the algorithm to have two-sided error, meaning that it's allowed to occasionally give false positives and it's allowed to occasionally give false negatives. We just require that on each input, the algorithm gives the right answer with high probability. Similarly, we would like to design deterministic log space algorithms for languages in BPL. Recall that BPL is defined just like BPP, except that instead of randomized polynomial time, we're talking about randomized log space. The popular conjecture says that both of those derandomization goals are always possible. That is, it's conjectured that P equals BPP and L equals BPL. Informally, these conjectures are saying that randomness is not necessary for efficient computation. Right? For every clever randomized algorithm, there's an even cleverer deterministic algorithm that does the same job. There's no need to toss coins. So you might as well throw all your coins in the trash. Let's talk about how one might hope to prove P equals BPP or L equals BPL. A pseudorandom generator is a powerful tool for derandomization. It's an algorithm that stretches a short, truly random d-bit seed out to a long pseudorandom n-bit string. The guarantee is that for every function f in some class script f, the expectation of f on the pseudorandom distribution is within plus or minus epsilon of the expectation of f on a truly random input. Therefore, by trying all seeds of the pseudorandom generator, we can deterministically compute the expectation of f to within plus or minus epsilon. Here's the connection with derandomization. Suppose f computes the output of a randomized algorithm as a function of its n random bits. Then the expectation of f is the acceptance probability of the algorithm. Therefore, a suitable pseudorandom generator implies P equals BPP and L equals BPL. Unfortunately, though, designing good pseudorandom generators has turned out to be extremely difficult. That's one reason that researchers study algorithms with one-sided error. Recall that RP is defined like BPP, except that when the input is not in the language, we require that the algorithm always rejects. That is, the algorithm has no false positives. Clearly, RP sits between P and BPP, so derandomizing RP is potentially easier than derandomizing all of BPP. Similarly, RL is the one-sided version of BPL. Here's a natural approach to derandomizing algorithms with one-sided error. We could try to design a hitting set, which is a one-sided version of a pseudorandom generator. A hitting set is a set of n-bit strings such that for every function f in some class, if the expectation of f on a truly random input is at least epsilon, then there is at least one string in the hitting set that f accepts. By plugging in all strings from a hitting set, at least we can distinguish the case that f always rejects from the case that the expectation of f is at least epsilon. And if I don't specify a value for this threshold parameter epsilon, if I just say a hitting set, by default you should assume that epsilon is 1/2. Hopefully it's clear that a suitable hitting set would immediately imply a derandomization of algorithms with one-sided error. For example, if there is a polynomial time computable hitting set for size n circuits, then P equals RP, right? Because you can just try all strings in the hitting set and see if any of them cause the algorithm to accept. The interesting thing is that it's actually possible to do more with hitting sets. If you get creative and you do something smarter than simply plugging in all the strings, you can derandomize more algorithms. In fact, there's a theorem first proven by Andreev, Clementi, and Rollum that says, if there's a hitting set for circuits, then not only does P equal RP, but also P equals BPP. So even though the definition of hitting sets is one-sided, they are sufficient for derandomizing algorithms with two-sided error. What about derandomizing log space algorithms? Again, it's immediate from the definitions that a suitable hitting set would imply L equals RL.
This time, we should assume a hitting set for a model of computation called width-n read-once branching programs. I'll describe the model on the next slide, but the point is, it captures the action of a log space algorithm on its random bits. Okay, the main result of this work is that if there is a log space computable hitting set for width-n read-once branching programs, then not only does L equal RL, but also L equals BPL. So just to be clear, when I say the hitting set should be log space computable, I mean there should be a log space algorithm that enumerates all the strings in the hitting set. In particular, the hitting sets we're talking about therefore only have polynomial cardinality. Here's an equivalent way to rephrase our theorem. If there's some black box way to de-randomize the promised version of RL, then L equals BPL. Thus, our theorem is a connection between one-sided and two-sided de-randomization of space-bounded algorithms. Here's the definition of the read-once branching program model. A read-once branching program is a directed graph consisting of n+1 layers of vertices, v0 up to vn. The number of vertices per layer is called the width of the program. Each vertex has two outgoing edges pointing to the next layer, labeled 0 and 1. The program starts at a designated start vertex in the first layer, and it reads an input string from left to right to decide which outgoing edges to take. The program accepts or rejects depending on whether it arrives at a designated accept vertex in the last layer. In this way, the program computes a Boolean function on n bits. Like I said, these programs can compute the output of a log space algorithm as a function of its random bits. Each vertex of the program corresponds to a configuration of the log space algorithm. I want to emphasize that this model is read once. That is, it only sees each bit of the input a single time. If you're a randomized small space algorithm and you're wondering about a coin toss that happened 10 minutes ago, well, you should have written it down at the time. This is the crucial difference between BPL and BPP. Like I mentioned, it was already known that hitting sets for circuits de-randomize BPP. You could try to adapt the proofs of that theorem to the log space setting, but you'll find that they would require a hitting set for read-many branching programs, even though we're only trying to de-randomize read-once branching programs. That's why we need a new approach to prove our theorem. We're merely assuming a hitting set for read-once branching programs. Before I get into the proof, though, let me give you a little bit of context. Along with pseudorandom generators and hitting sets, there is a third important concept called a pseudorandom pseudodistribution. This notion was introduced a couple of years ago by Braverman, Cohen, and Garg. Basically, it's a generalization of the pseudorandom generator concept, where now we allow the probabilities to be arbitrary real numbers that might be negative or bigger than 1. Notice that this is a two-sided tool. It immediately allows us to estimate the expectation of f to within plus or minus epsilon, just like a genuine pseudorandom generator. Furthermore, the support of a pseudorandom pseudodistribution is automatically a hitting set. Thus, we have a hierarchy. Pseudorandom generators imply pseudorandom pseudodistributions, which imply hitting sets. For this reason, pseudorandom generators are the gold standard. Pseudorandom pseudodistributions are intermediate, and then a hitting set is the least desirable of the three. Here's the current state of the art for fooling width-n read-once branching programs. The best pseudorandom generator is still Nison's generator from 30 years ago, which has seed length log squared n plus log n log 1 over epsilon. However, a couple of recent papers have constructed pseudorandom pseudodistributions that are superior when epsilon is very small. And then another recent paper constructed a hitting set with even a slightly better space complexity. Now, like I said on the previous slide, pseudorandom pseudodistributions are superior to hitting sets in a qualitative sense. However, the present work narrows the gap between the two concepts, right? Because we prove that an optimal hitting set is sufficient for de-randomizing BPL, and that was the main purpose of a pseudorandom pseudodistribution in the first place. Let me also quickly mention that there are lots of cases where there has been more success constructing hitting sets than constructing pseudorandom generators or pseudorandom pseudodistributions. For example, linear threshold functions, width-3 branching programs, sparse polynomials, combinatorial rectangles, regular branching programs. So constructing hitting sets really is often much easier than constructing pseudorandom generators. That's why we want to design algorithms that use hitting sets without the need for pseudorandom generators. All right, without further ado, let me tell you the proof of our theorem. So let f be a width n, length n read-once branching program, and let t be polynomially larger than n. We'll use a hitting set consisting of strings of length n cubed t, so considerably larger than n. And using this hitting set, we'll estimate the expectation of f to within plus or minus epsilon. This will immediately imply L equals BPL. So I just need to explain how to use these bit strings of length n cubed t to come up with an estimate for the expectation of f. The idea is we divide each such string into n squared segments. There is one segment for each vertex in the branching program. I'll use this notation x bracket v to denote the segment of x associated with vertex v, which is a bit string of length nt. We're going to use this segment to try to estimate the probability of visiting v when f reads a truly random input. We denote this probability by p sub arrow v. Now let's zoom in on a single segment. We further subdivide the segment into t sample inputs, each of which is an n-bit string. I'll write x bracket v comma j to denote the jth sample input associated with vertex v. The point of these sample inputs is we'll use them to try to estimate the probability of visiting v. We define the estimated probability of visiting v to be the fraction of sample inputs associated with v such that when f reads that sample input, it visits v. We denote the estimated probability of visiting v by this symbol p hat sub arrow v. This estimate is a function of the bit string x, but we often omit the dependence on x as a shorthand. Here's an illustration of the definition. Let's say we're considering this red vertex v in the middle of the program. And let's say there are just two sample inputs. When the program reads the first sample input, it passes through v. But when the program reads the second sample input, it doesn't pass through v. That means the estimated probability of visiting v is 1/2, because half of the sample inputs cause the program to visit v. Ideally, we are hoping that these estimated probabilities are accurate, meaning that each one is close to the corresponding true probability of visiting that vertex. The estimates might not be accurate, though, and we can't directly check whether they are accurate. After all, the whole problem we're trying to solve is, of course, to compute the true probability of visiting the accepting vertex. What we can do, though, is check whether the estimated probabilities are at least locally consistent with one another. Here's what I mean. Define the transition probability from u to v to be the probability of reaching v when you start at u and read uniform random bits. This is denoted p sub u arrow v. We can express the true probability of visiting a vertex v in terms of the probabilities of visiting the vertices in the previous layer. Right? It's the sum over u of the probability of visiting u times the transition probability from u to v. Okay, so we say that a string x is locally consistent if for every vertex v, the estimated probability of visiting v is approximately the same as what you'd expect based on the estimated probabilities of visiting the vertices in the previous layer. Quantitatively, I'll say x is locally delta consistent if the consistency error is at most delta. Okay, and so just to emphasize, these transition probabilities that appear in the definition of local consistency, they're just between two adjacent layers. So each one is 0, 1/2, or 1, depending on how many edges there are going from u to v. Here's our derandomization algorithm. Find a string x in the hitting set that is locally consistent to within error epsilon over n squared. We'll have to prove that such a string always exists, but for now, let's just suppose we've found one. Then we output the corresponding estimated probability of visiting the accepting vertex. That's it. That's our estimate for the expectation of f. So let's quickly analyze the efficiency of this algorithm. Remember, we're assuming that h can be enumerated in log space.
Furthermore, for each string x, each estimated probability of visiting a vertex can be computed in log space just by feeding the sample inputs into the branching program one by one and seeing what happens. Therefore, the local consistency test can be computed in log space. Note that doing so requires reading the bits of x multiple times, but that's okay, we can recompute the bits of x whenever we need them. So anyway, that shows that the whole derandomization algorithm runs in log space. So now I just need to convince you that the algorithm is correct. To prove that the algorithm is correct, we need to show two things. First, we need to show that there is some string in the hitting set that is locally consistent. And second, we need to show that if a string is locally consistent, then it gives an accurate estimate for the expectation of f. Let's start by showing that some string in the hitting set is locally consistent. To prove this, we're of course going to use the hitting property of h. It's tempting to think that the claim is immediate, because after all, h is a hitting set for small space, and the local consistency test runs in small space. That argument doesn't work though, because the local consistency test reads the bits of x multiple times, and h is merely guaranteed to hit read once branching programs. So we need a different argument.
Here's what we do. Say x is gamma accurate if each estimated probability of visiting a vertex is within gamma of the true probability of visiting that vertex. If we pick x uniformly at random, then with high probability, x is accurate to within error epsilon over 2n cubed. After all, when x is random, we're just plugging a bunch of independent random samples into f and seeing what fraction caused the program to visit v. So we can apply Hoeffding's inequality. This is why we chose t, the number of sample inputs per vertex, to be roughly n to the sixth over epsilon squared. That's enough samples to get estimates that are accurate to within plus or minus epsilon over 2n cubed. Furthermore, I claim that there is a polynomial width read-once branching program, G, that checks whether x is accurate. This actually follows easily from the definitions, right? G just simulates f on each successive sample input, and it counts how many sample inputs for each vertex v cause the program to visit v. And then G just compares this count to the true probability of visiting v. So the crucial point here is that we can just hard code in the true probabilities of visiting all the vertices. Remember, we're just designing this branching program G for the sake of analysis. There's no need to algorithmically construct G, we're just arguing that it exists. That's why it's legal to use the true probabilities of visiting the vertices as part of the definition of G. Anyway, then G just needs one more state to indicate that it has, previously found some inaccurate estimate, and so it's going to ultimately reject this string x. Altogether, that's a polynomial width read-once branching program. On the previous slide, we already argued that a random string is accurate with high probability. So in other words, this read-once branching program G has a high expectation. So therefore we can apply the hitting property. We're guaranteed that there is some string x in the hitting set that is accepted by G. In other words, there is some string in the hitting set that is accurate to within error epsilon over 2n cubed. It should come as no surprise that if x is accurate, then it's also locally consistent. Let's do the calculation to prove it. On the left side here, we have the local consistency error at some vertex v. This is what we want to bound. Let's use the triangle inequality to introduce the true probability of visiting v. Now inside the second term, we can express that true probability of visiting v in terms of the true probabilities of visiting the vertices in the previous layer. Now remember, we're assuming that x is accurate to within error gamma. So each of these differences between estimated probabilities and true probabilities is bounded by gamma. Finally, these are probabilities, so this whole quantity in parentheses is at most n plus 1, or let's just say at most 2n. So that shows that accuracy implies local consistency, with a factor of 2n loss in terms of the error parameter. So that shows that there is a string in the hitting set that is locally consistent. So we're done with the first part of the correctness proof. Now let's show that if x is locally consistent, then the estimated probability of visiting the accepting vertex is accurate. In fact, we'll show that all the estimated probabilities of visiting vertices are accurate. To prove it, assume x is locally delta consistent. I claim that in layer I, the sum of the errors is at most n delta I. Let's prove the claim by induction on I. So we're starting at the beginning of the program and working our way to the end of the program. The base case I equals 0 is trivial because by convention, the estimated probability of visiting the start vertex is 1, and the estimated probability of visiting the other vertices in the first layer is 0. All right, so now let's do the inductive step. We need to bound the sum of the errors in layer I plus 1. Using the triangle inequality for each vertex v, we can introduce this inner sum. This inner sum is what you'd expect the probability of visiting v to be based on the estimated probabilities of visiting the vertices in the previous layer. Now, the first term on the right-hand side is exactly the local consistency error. So by assumption, it's bounded by delta. Meanwhile, in the second term, we can do a similar trick as before. We express the true probability of visiting v in terms of the true probabilities of visiting the vertices in the previous layer. All right, now we can pull this delta outside the sum, picking up a factor of n in the process. And in this second term, let's use the triangle inequality to move the absolute values inside the sum. Okay. Now let's interchange the order of summation. That way, when we look at the inner sum, we've fixed some vertex u in layer I, and we're looking at the sum of the transition probabilities from u to the layers to the vertices in layer I plus 1. Well, it's a probability distribution, so the transition probabilities sum to 1. Therefore, we can actually just drop that inner sum. Well, now this sum that we're left with is exactly the quantity that we're bounding by induction. So that completes the inductive step. We've shown that when we move from one layer to the next, the sum of errors increases by at most n delta. That completes the proof of this claim. Now let's consider the last layer, the case I equals n. This claim shows that the sum of the errors in the last layer is at most n squared times delta. In particular, it follows that the error at the accepting vertex is at most n squared times delta. In our algorithm, we had set delta to be epsilon over n squared. So that shows that the output of our derandomization algorithm is correct, i.e. it's within plus or minus epsilon of the expectation of f. That completes the proof of correctness of our algorithm, and it completes the proof of our main result. In the remaining time, let me tell you a little bit about a couple other theorems we prove in the paper. The first theorem is about constant width branching programs. Now, the algorithm I showed you earlier is non-black box, right? Because we needed to look at the branching program in order to test for local consistency. That means that the algorithm I showed you is meaningless in the constant width setting, because if we're given direct access to a constant width read-once branching program, it's trivial to compute its expectation to high accuracy. To address this shortcoming, we prove the following theorem in the paper. So assume there are log space hitting sets for constant width branching programs. And then suppose we merely have black box access to some constant width branching program f. So we can just make queries to f. We can't look at the underlying edges and vertices of f. Nevertheless, we show that under these assumptions, it's possible to deterministically estimate the expectation of f to within a small additive error in logarithmic space. The proof of this theorem actually uses totally different techniques than the algorithm I showed you earlier. This theorem is incomparable to our main result because, on the one hand, it gives a black box algorithm, which is better. But on the other hand, the space complexity of this algorithm has a poor dependence on the width of the branching program. That's why here I'm focusing on the constant width setting. We also prove a negative result in the paper. This one is a little meta, so it might take a moment to digest. Consider the setting of constant width large alphabet read-once branching programs. The theorem says, assume that in this setting, hitting sets and pseudorandom generators are equivalent. That is, assume that for every explicit hitting set, there's an explicit pseudorandom generator with similar parameters. Under that assumption, we prove that there exists a very good pseudorandom generator for constant width branching programs. That is, we use the assumed equivalence between hitting sets and pseudorandom generators to construct a pseudorandom generator with seed length log to the 1.001n. I mean, the exponent 1.001 can be replaced with any constant bigger than 1. So here's our interpretation of the theorem. It would be wonderful to have a reduction that says hitting sets are equivalent to pseudorandom generators, but in light of this theorem, it's probably not wise to try to prove that the two are equivalent, because it's at least as hard as constructing a good pseudorandom generator outright, which is a challenging problem that researchers have been working on for decades. Of course, if you're more optimistic, you might say that's all the more reason to try to prove the equivalence. It's an approach for constructing new pseudorandom generators. Realistically, though, I don't think it's a good approach. I'll wrap up by mentioning a couple of open problems. Hitting sets are arguably the most natural approach to proving L equals RL, and in this work, we showed that hitting sets would derandomize BPL as well. In principle, though, there could be a totally different proof that L equals RL, using non-black box techniques. Does any derandomization of RL automatically imply L equals BPL? We can make the problem easier by strengthening the assumption. Does L equals NL imply L equals BPL? Anyway, thanks for watching, and please don't hesitate to contact us if you have any questions or comments.